Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're looking at examples solving for shear stresses in beams. The next example, we're looking at a T-section with the geometry as shown in the figure. This is a problem from Mechanics of Materials by Timothy Philpott, Wiley, 3rd edition. The internal shear force V at a certain section of an aluminum beam is 8 kilonewtons. Let's go ahead and record that as a given. V equals 8 kilonewtons. And given the cross-section shown in the figure, determine the shear stress at point H, which is located 30 millimeters above the bottom surface. Here's the point H on the cross-section. We'll say find tau sub H. In part B, we're asked to evaluate the maximum horizontal shear stress anywhere in the T-shape. We'll call that tau max. And as we recall, that occurs at the neutral axis, or the centroid. In both cases, we'll evaluate the shear in units of megapascals. Okay, the first step for this problem would be to evaluate the centroidal location and the moment of inertia. Since we know how to do this for an unsymmetric section, I will summarize the calculations rather quickly. We'll break the section into two pieces. The top piece, which is the flange, and everything below the top of the flange, which we'll call the stem, usually the web. In this case, we'll call it the stem. To compute the centroid, we take a reference axis from the bottom, and here's a summary of the calculations. For each shape, we compute the area of the shape, so the flange and the stem. We compute the distance y sub I from the bottom to the centroid of that shape, and we multiply them together. Here's the sum of the areas, overall area, and the sum of y sub I times a sub I. The overall centroid being this number divided by the area gives us a value of 54.4, and that locates the centroid from the bottom. So I'll denote that right here on my figure. About 54.4. We've also computed the distance from the centroid to the top of the shape, which is 75 minus 54.4. We actually won't need that for the rest of the problem, though. The next step, to evaluate the moment of inertia, we apply the parallel axis theorem. To summarize the calculations here, we compute I for each shape about its centroidal axis. We compute the distance from the overall centroidal axis to the centroid of that shape. We call that d for each piece. We compute d squared times the area of each piece, and then we add together I plus d squared a for each piece, and the sum is the overall moment of inertia. And I'm not going to carry out that many significant digits. Let's call it 398,000 millimeters to the fourth. Next, let's proceed with our calculations. First, we want to evaluate tau sub h. Remember the formula, tau equals VQ over IT. We need to find Q for the section considering shear at point H. I'll draw a picture so we can do that. First thing, locate the overall centroidal axis. We have point H here, which is down. We remember that point H is 30 millimeters. So since the overall centroid is 54.4, this distance from the neutral axis down to the area where we want to calculate is 24.4 millimeters. The width here is 5 millimeters. And the centroidal distance down from the neutral axis to the centroid of that area, y bar equals 24.4 plus half of 30, which is a total of 39.4 millimeters. So Q equals y bar times A for the area indicated, 39.4 millimeters times 30 times 5 millimeters squared for the area, and this computes to 5910 millimeters cubed. Now we have everything we need to calculate tau at point H, V of 8 kilonewtons or 8,000 newtons. Remember, for stress in megapascals, my working units are newtons and millimeters. Q, 5910 millimeters cubed. I, 398,000 millimeters to the fourth. And T, the thickness of the section where we want to evaluate the shear, is 5 millimeters. And that computes to 23.8 megapascals. This is my tau at point H. Next, tau at the neutral axis, or tau max. Almost the same procedure, the same calculations, but we evaluate Q using a different area. I'll draw a picture of the section again so we can evaluate it. Here's my neutral axis. Since we're evaluating shear at the neutral axis, we want to take the area above or below. In this case, I'll choose the area below because it's only one piece or one section. If I took the area above, I'd have to split it into two. So it's a little bit faster to do the area below. This total distance below the neutral axis, 54.4, the same as the centroid. 5 is the thickness. My units are all in millimeters here. Y bar is the distance down to the centroid of this shaded area, which is just a half of 54.4, 20 or 27.2. So Q, in this case, Y bar times A equals 27.2 millimeters times the area, shaded area, 54.4 times 5 millimeters squared. This computes to about 7,400 millimeters cubed. That's out to 3 significant digits. Tau equals VQ over IT, 8,000 newtons times 7,400 millimeters cubed divided by 398,000 millimeters to the fourth, and T again is 5 millimeters, computes to 29.7 megapascals. So one check here is a very simple check, but we expect the shear at the neutral axis to be larger than the shear at point 8. Quick inspection shows that indeed that is the case. Overall, just to give a little idea of how stresses vary over the cross section for a T section, we know it's 0 at the top of the flange, 0 at the bottom. We don't know how shear stresses vary through the flange, but through the web or the stem piece, they would look something like this. Maximum is going to be at the neutral axis. So, and quadratic variation, so, something like that. Should be quadratic all the way through, but kind of a bell shape, if you will. And here's the max, and here's the value at point H, which is slightly smaller, and throughout the rest, variation would be approximately as shown there. And that concludes this video.